remember, this is your inertial view. Okay? So what we did to get this picture of the view, of the motion, is we non-dimensionalize your angular momentum vector. So when you divide by the magnitude of your angular momentum, you get a unit vector. Okay? What we're calling u here. So then the precession of your angular momentum vector for constant transverse torque, your angular momentum vector will move, okay, in inertial space. That's this precessional locus. Okay? On top of that, you still have potential nutation. So your z-axis is going to be moving about in this circular motion as well. This is your nutation locus. Okay? And that circular motion transverses around wherever your angular momentum vector is. Okay? This is looking down on it, obviously. Okay? So this picture of the motion was derived using this equation.
Professor, real quick.
Yeah.
Just on that term, nx over c omega squared, is that raised to, just below it? Is
Right
that
here.
raised to the sigma minus 1? Or
No,
is
no,
that
just times.
just multiplied? Okay.
Yeah.
That's all.
Okay. So, for this picture, there were some assumptions made, namely that your initial conditions were 0, and also we assumed that there was no y torque. Okay? And our torque in the x direction was positive, if you remember correctly. Okay? So when you make those assumptions and the fact that it was a dish-shaped vehicle, you get this type motion. Okay? You make different assumptions, you will get different motion. Okay? And y, if you have a positive term there, and x goes to 0, I believe this shifts into this precessional being along the y-axis as opposed to x-axis. Yes?
So hx0 and hy0, those are the initial?
These are the initial conditions.
Okay, yeah.
So you have those embedded in here, similar to here, in the body equation.
We're assuming that
So we-
initially it's aligned with the z-axis?
Initially, yes, you're starting right here.
Starting there, all right.
Okay? So z and your angular momentum vector are both perfectly here. You fire your offset motor, and all of a sudden your angular momentum vector starts to precess. And you're going to get some nutation. Okay? So, if you had a rod-shaped vehicle, for instance, that change in assumption would cause these nutational locus circles to be on the inside. Okay? So based on your assumptions, your motion will be similar but different. Okay? Go back and review that. Any other questions about that before I move on? That's probably the most hard thing to conceptually get.
What lesson number had we refer back to?
Oh, I don't know. It was right before the midterm.
7, I think.
Yeah, it's like a few pages before. or after the-
Any other questions? All right. We briefly went over non-rigid spacecraft. What does non-rigid spacecraft imply? That you're going to have energy dissipation. So your kinetic energy is no longer a constant. Okay? So the time rate of change is going to have a value now. It basically means your spacecraft in an equilibrium spin about your maximum inertia axis It's gonna give you a T1 equal to A omega x squared all over 2, which can also be written as h squared of A. And likewise, if you have spacecraft, an equilibrium spin, inertia axis c, omega z squared is h squared over 2c. And so you know that T2 is greater than T1. How do you know that?